You have fallen into Event Horizon with John Michael Godier. Joining John today is Dr. Nour Raouafi. Dr. Raouafi is the project scientist of the NASA Parker Solar Probe mission. He has a PhD in astrophysics from the Université Paris-Sud. Before joining the Johns Hopkins Applied Physics Laboratory in 2008, he worked at the Turin Observatory in Italy, the Max Planck Institute for Solar System Research in Germany, and the National Solar Observatory. His research spreads over a wide range of social and heliospheric areas, with emphasis on the dynamic solar corona via the analysis of spectral and imaging observations, theory, and modeling. He contributed to diverse research areas, which include solar magnetic fields, spectroscopy, polarimetry, coronal plumes and jets, CMEs and coronal shock waves, solar wind, solar energetic particles, and cometary physics. He authored and co-authored tens of peer-reviewed papers and meeting proceedings. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Nour Raouafi, welcome to the program.
Thank you for the invitation. It's really a pleasure to talk to you about something very exciting this year, that is the Parker Solar Probe getting closest to the sun ever.
The Parker Solar Probe is the most harrowing mission that I've ever seen NASA do. In other words, not only is it the fastest thing that humans have ever created, but it is dipping into the solar corona. How close is the closest approach of the Parker Solar Probe to the sun's surface?
And that actually happened on a very special day. That will be the eve of Christmas of this year, that is December 24th. And Parker Solar Probe will get as close as 3.8 million miles from the surface of the sun. When we say 3.8 million miles, that sounds like a big number. But when you think of the Sun-Earth distance, that is 93 million miles, so Parker Solar Probe will be 4% of the Sun-Earth distance. It is almost touching the sun.
Now, when you make a close pass like that, what's it like communicating with the spacecraft? Because it would seem to me that the sun's going to interfere in that communication. So do you just have to download the data after the encounter?
That is actually what happens, because long before we get to that point, we cannot talk to the spacecraft. There is only a special way when the spacecraft every now and then, a couple of times, sent us what we call a beacon tone, and it's a very small bit of telemetry telling us that what is the overall state of the spacecraft. But other than that, we cannot talk to the spacecraft at all. And during that time, Parker Solar Probe has to face the sun on its own. If it encounters any type of problems, it has to solve it by itself. We cannot do anything to it.
Now, how does it do that? In other words, say it encounters something and needs to reorient itself. Is it just, is it a basic artificial intelligence?
It is artificial intelligence. It's autonomy. So we spent really years and years and years trying to think of every scenario, every potential problem that the spacecraft might encounter. And we basically built that into the spacecraft, and that's the spacecraft is fully autonomous. And it's not only that, the autonomy system on probe can keep the spacecraft going for a little less than 2 months without any human intervention. That is a long, long period. But still, it works without any problem so far.
Now, what is the mission duration? What was the original mission duration of Parker Solar Probe?
So a Parker Solar Probe has a prime mission of 7 years. We launched on 2018, that is August 12th of 2018. And by September of next year, the prime mission will come to an end. That is basically, we started from the solar minimum and will end at the solar maximum. But the spacecraft is very healthy right now. We don't track any life-limiting problems like that. So the hope after the prime mission is NASA will keep the mission going through extended missions. We will propose for it and we'll keep it going as long as possible.
Now, eventually, what happens to the probe after the extended missions and everything are finished and it's done? Is it eventually going to plunge into the sun, or is it just going to sit out there in a elongated solar orbit forever?
Believe it or not, getting close to the sun is not an easy thing to do at all. Although the sun has a huge gravity, but it's not really an easy thing to do. The reason for that is when you launch something from Earth, that object will inherit the orbital speed of Earth, and that actually prevents it from diving toward the sun. For Parker Solar Probe, the way we do it is we fly by Venus multiple times, and every time we fly by Venus, the spacecraft will slow a tiny bit, and that will let it dive a little deeper toward the sun. So the final orbits are pretty stable, and Parker Solar Probe will stay there for a long, long time. And eventually, when we end the mission, so we cannot control the attitude of the spacecraft anymore, and it will be wobbling, and sensitive parts of it will be exposed to the sun, and that will not work anymore. But the body of the spacecraft itself will stay there for a long, long time. But eventually, after tens and maybe hundreds of years, it will disintegrate.
Now, how do you keep the spacecraft cool? How do you deal with the intense heat from the sun that it's absorbing?
So, if you imagine the hottest summer, the hottest day in the summer here on Earth, Parker Solar Probe, when it is closest to the sun, it will be exposed at about 500 times the heat we receive here on Earth. It is extremely, extremely hot. But the way we do it, we have thermal protection system, which is the heat shield that is in front of the spacecraft, at top of the spacecraft, and that's actually what stands between the heat of the sun and the main body of the spacecrafts and the instruments. So the heat shield itself is made out of carbon foam, and it is 4.5 inches thick. When the spacecraft fly closest to the sun in December 24th, the side facing the sun would be glowing at more than 2,500 degrees Fahrenheit. The backside of the TPS, which is just 4.5 inches back, will be at about 700 degrees. And the magic is one yard behind that, it will be room temperature. And it's there where the spacecraft and most of the instruments are residing and operate at room temperature. So all of them are protected by the shade cone of the TPS, the thermal protection system, which, as I said, it stands between the sun and probe itself.
What's it made out of, the shield?
So, although I cannot tell you how it is fabricated because it's a secret, but if you look at the shield itself, it is basically a piece of carbon foam. That's what it is, and it is sandwiched between two layers of carbon composite. And that's what it is. The other thing that we have on Parker Solar Probe, that on the side facing the sun, we also have a very special plasma spray that was done specifically for Parker Solar Probe. And obviously it has the white color for obvious reasons. We want to reflect as much light from the sun as possible to deep space.
Now, when you actually cross into the corona, which I think isn't that the Alphen surface, I think it's called?
Alphen critical point, or Alphen surface, yeah.
Yeah, so what's it like when you go in there? What is the measurement when you're outside of it versus the measurements on the inside?
So the Alphen critical point, or boundary, if you will, it is so important because it separates the solar corona that we see during the total solar eclipse from the solar wind that engulfs all the planets of the solar system. And the physics on either side of it is slightly different. So in the solar corona, the magnetic field is so strong, so the whole corona will rotate with the sun as a rigid body. On the other side, the magnetic field is weaker, starts weakening, and basically the plasma, the gas, will dominate the physics. Also below the critical point, it's there where most of the acceleration of the solar wind occurs. And that's the main reason why we want to fly through it as much time as possible below the critical point to understand how the solar wind comes about, how it is accelerated, and how the particles gain so much energy.
What have you learned so far about that, the generation of the solar wind? What has Parker revealed?
So one of the key observations that Parker Solar Probe provided is what we call the switchbacks. And let me tell you a little bit of history about it. This is the very first set of data we received back in 2018, and it showed something that we did not really see before. What we saw there are very large amplitude oscillations in the magnetic field. Just for the history, when we saw them, some of us thought, there might be probably something wrong with the instrument. And it took us just probably 10, 15 minutes to realize that the instrument is working perfectly fine. There is absolutely no issue with it. It's working as designed. And what we are seeing is something new that we did not see before. And actually what we are seeing are kinks in the magnetic field. The magnetic field will rotate all the way back to the sun and out, basically forming an S shape or a switchback, like a mountain switchback. And the nice thing about this observation is that close to the sun, we observed a gazillion of them. They are all over the place. And also they come in groups. They don't come isolated, or they are organized in some way. So trying to understand where the structures are coming from and how do they form and what do they do in the solar wind led us actually to the base of the solar corona, where the solar wind is coming from. And what we found there is you have very magnetic field activity at very, very small. It's basically you have very small explosions, like very small flares, but these are all over the surface of the sun. And each one of them will give you a tiny jet of plasma. We call them jetlets. And it's basically like you have a shower head all over the surface of the sun, and it is throwing jets of hot plasma all over the place, and collectively these jets or jetlets, they form the solar wind as we know it. And this is probably one of the best discoveries, the most significant discoveries that we've made over the last couple of years.
Now, as a hypothetical, of course, the sun can have coronal mass ejections.
Correct.
and flares and things like that. What dangers do those pose to the spacecraft should it by chance get hit?
So one of the science objectives of the Parker mission is we want to understand the acceleration of these hazardous particles that we call them solar energetic particles. Whenever you have an explosion on the sun, like a flare or a CME, they accelerate a tiny population of particles to a good fraction of the speed of light. And these particles are the hazard to humans in space, to space equipment like the GPS, satellites, or communication satellites. And when events are severe enough, their effect can reach us here on the ground, like affecting the power grid and all that. So these are the driver of what we call space weather. We want Parker Solar Probe to fly as many of these events as possible and to cross in particular the sites where the acceleration occurs. It's where these shock waves take place, are occurring. So far, Parker Solar Probe flew through several of them. Most of them are, I would say, on the lower end in terms of speed. But there are a few of them, they were pretty violent. And one of them in particular occurred on September 5th of 2022. And Parker Solar Probe was very, very close to the sun. That event was flying at more than 2,500 kilometers per second. And Parker Solar Probe flew through it safely without any issue at all. The data we gained from that event and others give us some new insights into the physics of coronal mass ejections and the acceleration of these particles. We are getting a lot of new insights into this. And Parker Solar Probe is designed for this. We want as many particles and as many events as possible, and particularly the most violent ones, to fly and hit Parker Solar Probe, in particular when it is very close to the sun.
Now, the namesake of the Parker Solar Probe, it's named after Dr. Eugene Parker, who was, as I recall, the discoverer of the solar wind, under much controversy when he originally proposed it, as I recall.
Yes.
What was that story? And did you know Dr. Parker?
Oh yeah, I knew him. I first met him in the early 2000s when I was still a student. And Gene Parker is an out-of-the-world guy. I mean, he's an amazing scientist, and more than that, he's a great human being. And naming the spacecraft a mission like Parker Solar Probe like him is just an honor to him, and it's really honoring his legacy in a way. And the nice thing about it also that NASA made it the first to name a space mission after a living human being. NASA has never done that. We've done it for Parker Solar Probe, and actually, Gene Parker attended we had the ceremony for renaming the spacecraft, and he was there. He came to EPL and saw the spacecraft being built, and he was at the launch as well. And after that, we met several times with him to update him about some of the results we are getting. Yeah, Gene Parker, back in 1958, wrote a paper which is pretty controversial. The paper basically saying, okay, you have this gas, this boiling gas in the solar corona, which is multi-million degree hot. It cannot stay static. Some of it has to fly away from the sun and create a breeze or something. He called it the solar wind. But when he sent his paper for review, many reviewers basically ridiculed him, and some of them told him that he might actually go to the library to read about the sun and the solar corona in particular. But we were so fortunate that the editor of the Astrophysical Journal was no one else than Chandrasekhar, the Nobel laureate. On his own, at a certain point, he decided to publish the paper. And the anecdote says that he told Gene Parker, Gene, this might be a ridiculous idea, but I'm going to publish it anyway. The rest is history. 4 years after the publication of that paper, Marshall Nigebauer, another great scientist, confirmed the existence of the solar wind from measurements of the Mariner 2 mission. And from there on, the solar wind is there, and it's one of the most mysterious phenomenon of solar and stellar physics.
I always found that part of the story particularly appealing, that one of the great physicists, Subrahmanyan Chandrasekhar, forced it through.
Exactly, yeah. I believe greats recognize each other.
I believe so, but it wasn't long, as I recall, before he was proven right. Just a few years, wasn't it?
Yeah, just 4 years afterwards, he was proven that the solar wind is there. But the solar wind that we measure up there, it's way, way more complex than the simple theory, the relatively simple theory that Gene Parker put together. But that does not really take any credit away from a Parker model. It is a pioneering idea that he put out there, and it opened the gate for a totally new field of research in space physics.
Now, with the probe, communications again. So what does the downlink look like? In other words, when you can get the data, I mean, how long does it take, and at what point is it in its orbit when you can actually retrieve the data?
It really depends orbit by orbit. It depends a lot on the geometry, where the spacecraft is relative to the sun, and also where Earth is. And the reason for that, since we want to keep the spacecraft pointed at the sun all the time, the high gain antenna, we don't really have much room to maneuver it to look at the Earth all the time. So we have certain periods of times when we have a clear view of Earth, and it's then when we can start talking to the spacecraft and bringing the data down. So for some orbits, we have a lot of time where we can bring the data down, and usually we bring a ton of data. I think on average, we are bringing three times more data than what we predicted pre-launch. But there are also some unique orbits where we don't have any downlink at all. These are rare, but they are there, where the geometry doesn't allow us to talk to the spacecraft at all. What we do then is store the data on the spacecraft and wait until the next opportunity to bring it down and work on it.
Now, the intimate involvement with the planet Venus that Parker Solar Probe has, what science can be done at the Venus passes?
That's really that's an excellent question. So whenever we fly by Venus, we have all our instruments on and collecting data about the Venus environment, and there are in particular some flybys where we fly behind the planet. On the night side of the planet, it's like we have Parker Solar Probe is having an eclipse at that time. These flybys are probably the most interesting ones. Because with our imager, WHISPER, we can look at the backside of the planet and try to figure out what is going on there. And obviously, we have the in situ measurement that are measuring the properties of the plasma in there. So from WHISPER, for example, what we learned a lot about the surface of Venus from the couple of flybys we had. One of them in particular is that we discovered a new wavelength. It's an emission from the surface of Venus that nobody has seen before. And it's actually the shortest wavelength of thermal emission from the surface of Venus. So what WHISPER is telling us from that is basically telling us there is a new window to observe and study the surface of the planet using that wavelength. And that's the record so far in terms of the shortest wavelength of the thermal emission from the surface of Venus. From that, using this observation, we can also learn about the composition, the rock composition of the plateaus. It's not detailed composition, but still we have very good ideas, and this information will be useful for future missions that are dedicated to Venus. On November 6th of this year, we will fly by Venus for the 7th and last time of the prime mission of Parker Solar Probe. And this flyby is very unique. Very unique because, it has also an eclipse. We will fly through the night side of the night side of the planet, but also it is the closest to the surface of the planet than any other Venus flyby before it, for Parker Solar Probe, I mean. So we will be about 380 kilometers above the surface of Venus. We are going to collect a ton of data about the surface of Venus using the imager, but also the in situ instruments. We will collect a lot of data about the ionosphere of the planet itself and the induced magnetosphere as well. Since we are flying so deep into the atmosphere of the planet, these measurements will be very, very unique, and we really cannot wait to get them and look what is going on there.
Now, each of the instruments, the 4 major instruments on the probe, tell us about each one and what they're specifically measuring, what they do.
So let me start by, since I talked about WHISPER, the imager. WHISPER is a white light imager, and since we cannot look directly at the sun for obvious reasons, because we cannot expose the instruments directly to the sun, they will not work. So what WHISPER does, it looks to the side of the sun, and basically what it imaged the solar wind as it accelerated from very low down close to the sun and all the way past Earth. That's what WHISPER does. It's all, and the wavelength that it covers, it's between 4,500 to 7,500 angstrom. It's all one band that we observe the solar wind in there. Then we have also the fields suite. It has magnetometers. 3 of them, they are on the boom behind the spacecraft, and these resides on the shadow of the spacecraft. They operate also at internal temperature, but we also have the antennas, 4 antennas that are mounted at the same level as the thermal protection system, the TPS, the shield. And these electric antennas are the only one, together with another instrument, the Faraday cap. They are the only instrument that are exposed to the full environment of the sun. All the other instruments are on the bus and they are residing in the shadow of the TPS. So fields provides measurements of magnetic fields, electric fields, densities, temperatures, velocities, and all the fluctuations of all these parameters. Basically, it's through this suite will give us a map of the different characteristics of the plasma that Parker Solar Probe is flying through. We have also sweep. Sweep measures the thermal solar wind, the normal solar wind that we just talked about, that Gene Parker theorized about 60 years ago. And there again, what we measure velocities, densities, temperatures, and many other properties like the alpha and waves as well, all sorts of waves, if you will. The 4th suite is ESIS. And ESIS measured the high-energy particles, the solar energetic particles that are hazardous to space equipment and the humans in space. That instrument will measure them from relatively low energy to pretty high energies and cover a wide range of energies for these particles. So in a way, when you take the suite as a whole, we have 4 suites of instruments. All together, they form they complement each other in a way that will provide us a clear picture of what is going on around the spacecraft, but also far away from the spacecraft through the remote sensing data.
Now, what exactly is an alpha wave?
Okay, if you drop a rock into a lake, you will see a ring of waves propagating outward. These are just waves on the water, you see them. But now, imagine that you have a magnetic field, and a magnetic field is like, it has the field, magnetic field lines, they are like strings. And if you perturb one end of the string, you will have an oscillation that is propagating along the string to the other end. The magnetic field behaves exactly the same way. When you perturb the magnetic field at the base of the solar corona, there are a lot of waves that will propagate outward to the solar wind. And the alpha waves are these disturbances of the magnetic field. They are typical of the magnetic field, and that's why Alfvén discovered them back in, I believe, in the 40s, and actually got the Nobel Prize for them.
Sun grazer comets, the detection of comets.
Yes.
Getting very close to the sun. Tell us about that aspect of the mission.
Let me go to another mission before I talk about Parker Solar Probe. The other mission is SOHO, the ESA NASA mission that launched in the mid 90s. And by the way, actually, I started all my career on SOHO. So SOHO holds the record of the number of comets discovered, the sun grazing comets. I believe now it has over 5,000 comets in its catalog. And these sun grazing comets, they are very small. Usually you see them only when they are very, very close to the sun. And oftentimes they have just one pass and they will just disintegrate. They will not get on the other side. So that's why we call them sun grazing comets. Parker Solar Probe is no exception. When we get close there, we see some of them. And so far we have a handful of them that we see that are going down all the way toward the sun, and they will evaporate completely, and will leave no trace at all.
When you get close to the sun,
yeah, that's one of the surprises that Parker Solar Probe, I would say one of the gifts that Parker Solar Probe gave us from the first orbit. So let me go back over 90 years ago. In 1929, there were scientists called Henry Russell, and he specializes in dust around stars. And he put out a theory out there saying, okay, because of the radiation pressure and the excess heat coming from the stars, the dust particles, when they get very close to the stars, they will just melt and disintegrate, and they will basically be cleaned out by the wind coming from the stars, but also other properties as well, other effects as well. So he came to the conclusion that there should be a region around the star that is completely devoid of dust. He called it the dust-free zone. And since other stars are pretty far away, people looked at the sun and they said, well, if the dust-free zone exists, it should exist around the sun. And we know that in the heliosphere, there is plenty of dust. And the good example of it is the zodiacal cloud that we see when the sun is setting. We see that light. It's the zodiacal light. It's coming from that cloud. But people looked for this dust-free zone around the sun for decades. And they did not really come to any firm conclusion about it. There are probably a hint here and there, but they were weak hints. Nobody can say for sure there is something there or not. What we thought about Parker Solar Probe said, okay, since we are getting really so close to the sun, we probably should, toward the end of the mission, the prime mission, we should have some hints about the existence of the dust-free zone. But from orbit 1, Parker Solar Probe gave us a very, very strong hint that the dust-free zone is there. And that's actually, we went on later on to confirm it, and it's there. And we know where it is now around the sun. And we learned so much more about the properties of dust around the sun.
What will the data set, the work of Parker Solar Probe, how can we apply that to astrophysics and stellar physics in general? In other words, what will it tell us about other types of stars?
Yeah, the sun is the closest star to us, and we observe it in so much details that we can never do that for another star. Well, I should not say never, but probably who knows, future civilization probably might come up with other genius idea that they can revolutionize everything. But the sun still, the amount of detail that we can observe it with is just mind-boggling. And we learned so much about it. What we can learn about the sun, we can project it on other stellar system out there in the universe, and basically that will be our messenger to the sun. In a way, is our gateway toward other stellar system in the galaxy, but also in the universe as well. And in particular, the stars that are of the same type of our sun, that are more or less the same size, and they have more or less the same evolution as the sun. So this is, for us, the sun is probably one of the gifts that nature gives us, which is which is actually next door to us, that we can learn so much about it. But there is another thing also that is so important for us to understand how the sun works. We talked about the solar wind. We talked about coronal mass ejections and energetic particles and all that. If you think of it, we human beings and Earth in general, we actually live in that flow on a daily basis, except that we don't feel it because we are protected by the magnetic bubble of Earth, the geomagnetic field of Earth, that we simply don't feel it, but we live on it. Now, the other importance of it, one might ask, okay, since we are protected by the geomagnetic field of the Earth, why one should bother to go so closest to the sun and look into all these technologies and invest all that much into it? There are a few things that pushes us. The first thing I would say, just the humans are curious by nature. We want to understand, but there are other needs as well. Now, by the end of the decade, we will send men back to the moon, and we will land women for the first time on the moon. And it's not for a short visit. The plan is to have a permanent presence there. And hopefully soon after that, maybe in the next couple of decades, we will also have the first human landing on Mars. So our presence in space is going to be more and more and more as we go. And we have to protect our assets and our astronauts and our scientists who are up there in space. We have to protect them. And we have to protect them exactly from the effect of the solar activity that drives space weather. And that is why we need challenging missions like Parker Solar Probe to go closest to the sun and providing us with understanding that was not available to us before, that will allow us to understand better how the sun works, and hopefully at a certain point try to predict what the sun is going to do at any given time.
That would be very useful, having some way of predicting the sun's weather.
Absolutely.
Now, the speeds involved with Parker Solar Probe as the fastest object humans have ever created, give us a sense of that. I mean, this is actually a non-zero, I think it's way below 1%, but we're getting into an actual speed of light fraction, a tiny fraction of the speed of light. So give us a sense of the speed.
So a probe is a fast-paced mission. It's when we talk about speed and other properties about Parker Solar Probe, these are big numbers. And honestly, when I tell you that, okay, when Parker Solar Probe is flying closest to the sun, it will be flying at 195 kilometers per second, or it is something like 430,000 miles per hour. Yeah, it's a big number, but our brains will probably cannot make sense of it. Now, to make sense of it, you imagine you pick a ride on Parker Solar Probe, and you are flying from the West Coast, let's say Francisco, to Washington, D.C. You will do that flight in about 20 seconds. That's how fast the Parker Solar Probe is. You can do Washington, D.C. to Tokyo in about a minute. This is why Parker Solar Probe, when it is flying so closest to the sun, is extremely fast, because it's basically it's swinging by the sun. The gravity of the sun will give it so much speed. And for the other thing that is also fascinating about this mission is that its orbit is pretty short. Its orbit is about 3 months. So every 3 months, we have a new load of new data, and it's just, we love it, but it's overwhelming as well. If you think of some other missions like planetary missions, they have cruise phases of years and years and years. When we launched Parker Solar Probe, our cruise phase was less than 3 months. That's all the time we had to commission the spacecraft completely, commission the instruments, and be ready to encounter the sun for the first time. And guess what? We better be ready, or probably everything would be lost, because the spacecraft was diving toward the sun no matter what, and it better work as we thought it should. And we were so fortunate that it worked like so beautifully.
Now, predicting the behavior of the sun, its weather, also relates to not just space, but Earth, the infamous Carrington event, and those sorts of things. So if that were to happen today, we would be in trouble. So that it's also very important to try, in a predictive path, to try to figure those out, right?
Well, let me tell you things. The scientist part of me, which is one of these events will occur one day, because we will learn so much from it. But now let me go to the other side, which is, any normal human being. If we get hit by one of these events, the damage estimate is in the trillions of dollars. It will take a long time to recover from it. Just let me give you examples. Like back in 1989, there was an event. It's not really a very big event. It caused a power outage in the northeast of America and Canada. And when you look at the movie of the power shutting down and progressing through these two countries, it is amazing to see it. When you look also at the movies of the 40 spacecrafts of SpaceX diving into the Earth atmosphere and burning there, seeing that view, it's fascinating. Space weather is a real thing there. And we cannot do anything about it, because the sun is so big, it's so huge. The sun will do what the sun wants to do at any given time. So our best way is to mitigate the effect of the sun, and the best way to mitigate it is to understand it and try to predict it. That's the best way. Now let me put one more thing, and I think I alluded to it before. Space weather, I think up to now, we think about space weather only when we think about the Earth environment around us. But now, since we are going to have a permanent presence on the moon, and as I said, hopefully after that will be Mars, space weather becomes a global thing. Here on Earth, we have the protection of the magnetic field of the Earth. It acts like a shield for us. Up there in the moon and Mars and elsewhere, there is no such protection. What could be a mild event here for us on the ground could be a severe event on the moon and elsewhere. And that's why we have to keep an eye always on the sun and try to predict what it's going to do, what will be the impact. And now the impact will be everywhere in space. It's not only the Earth environment.
Now, my last question for you today, Doctor, involves a long-standing mystery of the sun on why the sun's atmosphere is so hot. Are we going to be able to answer that with a Parker Solar Probe?
I think Parker Solar Probe, let me say, that's one of the central science questions for Parker Solar Probe, one of the science objectives of Parker Solar Probe. And with the data we are getting, we are really getting very unique insights that are guiding us toward more and more understanding of what is going on there. I talked about the generation of the solar wind before, and if you will, to explain the acceleration of the wind, the acceleration of the wind goes hand in hand with the heating of the solar atmosphere. And the coronal heating, if you will, it's so mysterious, because when you look at the temperature of the gas at the surface of the sun is what we see with the naked eye from the ground. The temperature there is about 6,000 degrees, or 10,000 degrees Fahrenheit. You go above about 2,000 to 3,000 kilometers, and the temperature of the gas will jump to over 2 million degrees Fahrenheit. And that is very counterintuitive. It's mind-boggling, because from everyday experience for here on Earth, if you have a source of heat like a campfire, if you move away from it, it cools down. But obviously, that is not the case for the solar corona. It gets actually much hotter, and that was discovered in the late 30s. And now we are trying we are still trying to understand it. As I said before, Parker Solar Probe is giving us strong hints about certain physical processes that are occurring there that will guide us to find an answer to that phenomenon. Let me say something about it, because the discovery of the coronal heating is kind of anecdotic. It actually has its roots in a total solar eclipse. It dates back to 1869. That is 1 decade after Carrington observed the white light flares, the Carrington event. There were two American astronomers. They want to observe that total solar eclipse. And both of them independently, they made exactly the same observation, the same discovery. And what they observed, there is a new emission of light from the solar corona. It's in the green part of the spectrum. To this day, we call it the green line. But the issue with that observation is nobody knew what was the chemical element that was responsible for that emission. That mystery lasted over 70 years. And at the end of the 30s, what we discovered is that it was iron ionized 13 times that was emitting that light. Iron has 26 electrons. Basically, you strip an atom of iron out of 13 electrons out of the 26, and you get the iron 13 plus. But this is the thing. That ion can only exist in multi-million degree hot plasma. And its presence in the solar corona means that the solar corona is multi-million degree hot. And that's how we came to discover the coronal heating. And from there on, the rest is history, and everybody is trying to understand what is going on, why the solar corona is over 300 times hotter than the solar surface. And by the way, this is not a unique problem to the sun. We also, there are other millions and billions of stars out there that also have corona, and also they have the same problem. So understanding the coronal heating and the acceleration of the wind on the sun will also help us understand other solar systems, and particularly if we are looking at how the stars shape their environment and their impact on the habitability zone around them. If we are looking for life elsewhere, the sun and the earth and the solar system are an excellent laboratory for us. Understanding what is going on in the solar system will help us understand other solar systems, and maybe one day answer the question whether there is life elsewhere in the universe.
I think the main question there is the red dwarfs and their flaring, and understanding the mechanisms for flaring may answer the question as to whether they actually bathe their planets in radiation like that from flares, or if it just misses completely and only comes out near the poles, which there is a paper out there on that.
Oh.
But by understanding the sun, that can answer that question, and that's a huge part of habitability.
Absolutely.
All right, Doctor, thank you for joining us today. I wish you great luck with the Parker Solar Probe, and I look forward to the science and the mission extensions. I bet they happen.
Thank you so much, and I would like to remind everybody of December 24, that is the eve of Christmas of this year. Parker Solar Probe will be flying by the sun, will be closest to the sun ever. It will be a first for all humanity. This is equivalent to the moon landing back in 1969, but this time around, we are going to embrace our star, the sun.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.